Dear students, in this video I am going to start interpolation, third unit. So in this unit we are having problem of the form this. We have basically data of the form x and f. X is having values like x0, x1, x2, xn, and the corresponding values of the function f is f0, f1, f2, fn. Okay, so what is the graphical way? Graphical way is like this. We have this data. Here we have x0, x1, x2, like that, x3, and somewhere is xn. On the y-axis here we have basically f of x. Here is x. Okay, so here the corresponding value of this is say f0, this is f1, this is say f2, f3, f4, n. These are the values f0, f1, f2, f3, fn. Okay, so now what is your target? Actually our target is to fit a polynomial or any other curve so that we can cover up all these points up to a desired degree of accuracy. Fine. So we have lots of options. Either we can join all these, because we have only these values. We don't have exact function f. We don't know about f. We have only these values with us. So now target is to cover up or to combine or to cover up actually all these values through a function, which is very difficult to find. This is not very easy to find exact f. That's why our target is to find the approximate function. For example, this is the exact function. Let's see. Say this is the exact function. For the simplicity, suppose this is the exact function. This is exact function f of x. This is the exact function. Cover up all the values. So you can see that this function f passes through all the points exactly. Here, exactly satisfies. Okay, but we don't know about this. We don't know. So what is our target is to fit a polynomial or a curve, any other function which cover up this or reach to these data points at a desired degree of accuracy. Fine. So basically what is our aim? Our aim is to approximate the value of f, this function, at some value of x not listed among the xi above. Okay, so this is our target. Or determine a function p that in some sense approximate the data. So our target is to fit basically approximate the value of f at some value of x not listed among. So for example, say here, so you want to find out the value of x here. Suppose this is the point. Here your target is to find out this value, but since you don't know about f, so how to find out this value? This is very difficult. Either you can approximate the function here or somewhere here. This will give you some error, because here you are having some more value than the exact value, and herein if you will get this result, then obviously you are getting less than the expected one. So in both these cases you are having some error, because the exact value is this, but either you can get this or this with the help of any other approximation. Okay, in the second, determine a function p that in some sense approximates the data. So what you will do, generally you will fit a polynomial which is nothing but the approximation of this function. For this approximation we have some methods how to get this approximate function, because if you are just fitting a polynomial here, then obviously we have certain methods. Okay, so we can fit basically any function or a polynomial here with the help of different methods. Okay, so what are the ways? So thus the above mathematical problem gives rise to two different area of study. One is interpolation, another one is approximation. So what is the difference? Let's see. What is interpolation? So in interpolation, a function p which is less expensive to evaluate or easier to manipulate is determined by requiring the error to be 0 at each of the xi. Xi means these node points. By xi, that is by enforcing, this is important, enforcing the conditions pxi is equal to fi for each I is equal to 0, 1 to n. What is the meaning? Meaning is that basically this is the exact curve. So here, since we don't know f, so what we will do, we are basically fitting a polynomial like this. If you will see this black curve, so you will see that this black curve is basically denoted by px. Exact one is denoted by this f of x, blue curve, and this black curve is basically the approximated curve. And you will see that the beauty of this px is that this px exactly satisfies this data condition. That means at xi, x naught, the value of p is also f naught. Here exactly you will see that this p is exactly satisfies at this point. Similarly, p goes exactly satisfy this point. That's why p and f both are intersecting at this point. So they will be same. Similarly here, f2 and p2 both are same. That's why we have this condition. So we can say that p at x naught is equal to f naught, p at x1 is equals to f1, and hence we can say that p at xi is equals to fi. Both are same, and this is for all I is equals to 0, 1 to n, and this is called as interpolating condition. Interpolating conditions. Okay, so hence interpolation treats error in a local fashion. Why this is local? Because this function, this p approximate curve or polynomial exactly satisfies the error, or there is no error at the node point, but there are error at the intermediate points. Here somewhere error is higher, somewhere error is low, but at the node points there is no error. That's why error is local in manner. Okay, second method is based on approximation. So approximation on the other hand treats error in a more global manner rather than local. Here we have local manner, here the error is global manner. So here what we will do, rather than this curve, we are taking like this error. We are not interested in that function will cover up all the node points. No, there is no need, but we are trying to reach like this. There is no such type of condition here, but we are trying to cover up most of the points nearby. So this is another way. So this is basically the approximation, and this P means interpolation. I think you understand the difference. Here we have satisfying this curve, this condition. That's why we get interpolation. And in the approximation, we are covering randomly by following certain method all the points, nearby all the points. And this is known as approximation. And approximation is done with the help of various techniques like regression technique in statistics, least square method, and so on. So what is the purpose? Purpose is that rather than choosing this condition here, our target is to minimize this P and P of xi minus f of I. This the difference, because here we have distance, we have certain distance here and here node points, they are not exactly satisfies. Okay, so what is our target is to minimize this. So if you minimize, for example, say square, then we have least square method. Okay, so this is the way, this is least square method, least square method. Okay, so this is one of the way. Okay, so this is the sum of measures, some measure of error. So this is the measure of error. Actually we are minimizing the difference and then it's square. This is one way, another maybe another way like that. Okay, and this is the sum. I think this is the summation and then square. So like that, or sum of, or they say the square and then summation. Okay, so this, so sum of the square of the difference between pxi and fi be minimized. So we have methods like least square method, least square regression method. Okay, but here our target is to cover up the interpolation rather than approximation. So what is the different types of interpolation? If this P you will take like a polynomial, then we are having polynomial interpolation. If you are taking rather than this P, you are covering some part by a one polynomial, another part by another polynomial, like that. This is called piecewise polynomial or spline interpolation. Okay, then rational interpolation, that means when P is basically a rational function, then this is rational interpolation. When P is basically a trigonometric function, then trigonometric interpolation. When P is an exponential function, then this is known as interpolation form. So here we will cover up these two, first two, polynomial interpolation and piecewise polynomial or spline interpolation. Okay, so in this study, in this chapter, we will cover up polynomial interpolation and piecewise polynomial interpolation. Okay, so let's see first part, polynomial interpolation. So before that, so there are three major reasons for focusing on interpolation by polynomials. Why we have selected polynomials or piecewise polynomial? Because the polynomials like Pnx is equal to a0 plus a1x plus anx raised to the power n can be evaluated very efficiently. Polynomials are easy to evaluate, or we can say that by following this condition we can easily find out the polynomial. That's why this is one of the reason why we have selected polynomial. Second is the derivatives and integrals of polynomials are easy to compute and are still polynomials. Third reason is polynomials satisfy the uniform approximation property. What is that property? Property is listed here. This is known as Weierstrass approximation theorem. What is the property? Which says that let f be continuous on the closed interval ab. Okay, then for given any epsilon greater than 0, there exists a polynomial p such that norm of p, f minus p, infinite norm, this is basically nothing but maximum of the magnitude of fx minus px, where x belongs to the closed interval ab, this should be less than epsilon. Okay, so if f is continuous in this closed interval, then if you take any epsilon, for any given epsilon, there exists a polynomial p such that the norm of f minus p, infinite norm of f minus p, is basically less than epsilon. This is the meaning. Okay, and this norm is basically, the definition of this norm is this: maximum of the maximum of this magnitude of fx minus px is less than epsilon, where x belongs to ab. Okay, so now here we are discussing since interpolation polynomial, so let us start with interpolating polynomial. So the first definition is interpolating polynomial. What is this p? P is known as this, the method is interpolation, but this px is known as interpolating polynomial. So first definition is interpolating polynomial. So a polynomial px is called an interpolating polynomial if the values of px and or its certain order derivatives coincide with those of f of x. That means satisfying this condition, the value of pxi and fi both will coincide for all the node points. This is the meaning. So if the values of px and or its certain order derivatives coincide with those of f of x and or its same order derivatives at one or more tabular points. Okay, so here we have taken only condition without derivative, but this may also be possible that p dash f of xy is nothing but f dash xi. So this is the condition for the derivatives. Okay, so both types of condition we have, without derivative and with derivative. Okay, so in general, if there are n plus 1 distinct points like x0, x1, x2, xn, here xn is nothing but b and x0 is nothing but a, closed interval ab, then the problem of interpolation is to obtain fx satisfying the conditions number 1. This is number 1 condition, which is pxi is equal to f of xi. That means this condition known as interpolating condition, where I is from 0, 1 to n. And the second type of condition is that here we have without derivative condition as well as with derivative condition. Here we have only without derivative condition. Here we have without derivative as well as with derivative conditions. Okay, for all from I 0, 1 to n. If you are having first type of condition, this, then the method of interpolation is known as Lagrange's or Newton interpolating polynomial. When you fit the polynomial, that means what is your target? Target is to find out p with the help of these condition. Then we have two methods to find out this p, and the methods are known as Lagrange interpolation polynomial and Newton interpolating polynomial. These are two methods. We will discuss these two. If you are taking the second condition, this, then we have one method which is known as Hermite interpolating polynomial. I think you understand. So for the first condition we have two methods, Lagrange and Newton interpolating polynomials. For the second condition, we have one method, Hermite interpolating polynomial. I think you understand. So we have discussed three methods. We will discuss three methods: Lagrange's, Newton and Hermite interpolating polynomials. Okay, the condition first give rise Newton interpolating polynomial, Lagrange's and Newton interpolating polynomial, and the condition 2 give rise to the Hermite interpolating polynomial. I think you understand the difference. So now before that we will discuss one theorem which is very important. Theorem says that theorem is basically related to the existence and uniqueness of px, which is very important, because if we have this data, these data points, and you are following any interpolation method, and suppose you have fitted this like this, this is your basically px interpolating polynomial, then what is the guarantee that we don't have any other px? because you are fitting a basically a polynomial. So maybe possible that you are having another px like that, like that. This is also satisfying all the conditions. This is also a node point. This is a node point, 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 this is a node point. So you will see that, so this is a P1, another black one is basically P2. This is P1 x, this is P2x. Both are interpolating. So what is the guarantee that we have a unique solution? Unique means we have only Px. We don't have any P1, P2, P3, P4. We will, so that's why we have uniqueness and existence. Existence and uniqueness of Px. That means if we have any data and we are following certain interpolation method, then generally we will have a unique polynomial Px. This will exist as well as unique. Both will. So this theorem will provide you a guarantee that for the certain data, and if you are following interpolation method, then polynomial will exist, and there is only one and only one polynomial. That means uniqueness. Okay, let's see. So assume that a function fx is continuous on an interval AB. Okay, so we will have that f of x is continuous in this interval. Further, assume that we have n plus 1 distinct points x0, x1, x2, xn minus 1, xn. Here x0 is nothing but a and xn is nothing but b of AB. So basically we will divide this interval into parts. Partition. We will do the partition through the points, and these are the points. And the values of a function f of x are known at these points. That means we are having basically what we have basically this data x0, x1, x2, xn. This is also known as a, this is also known as b. Okay, and at these point the value of the function f is known. That means this is known, this is known, this is known, this is known, and so on. In the intermediate, all these values are known. Okay, these dots represent that we have known information. So we seek to find the polynomial Px. Our target is to find a polynomial which cover up all these points. Okay, so let's see. The degree of the polynomial is say nth order polynomial. Because why we have taken nth degree polynomial? Because ultimately how many conditions are there? We have this f of xi. This is known to you for all I is equals to 0, 1, 2 to n. How many points are there total? For each I we have one value. So this is first, second, third. Similarly, this is xfn. So ultimately total, these are total n plus 1 points. And that's why we can fit a polynomial of degree n. Why? Because suppose we have a polynomial like this, a0 plus a1 plus x plus a2x square. It's a 2-degree polynomial. How many unknowns are there? a0, a1 and a2. So to find a0, a1 and a2 you need 3 conditions. So that you will have 3 equations, solve those equations and find out a0, a1, a2. That's why if you have n plus 1 points here, here is 3, here is 2. So if you have n plus 1 here, so there should be n. And that's why we are having n degree polynomial, because we have total n plus 1 points. So for n plus 1 points, we have n plus 1 conditions. and that's why we can fit a polynomial of degree n. This is the reason why we have taken nth degree polynomial, not n plus 1th degree. Okay, so the degree of the polynomial is n because we have total n plus 1 distinct points, that means n plus 1 conditions. Okay, which, and this polynomial, due to the interpolating condition, due to this interpolating condition, this condition, we have this condition pxi is equal to f of xi for all I 0 1 to n. Okay, so we have our target is to find out px, which is this polynomial satisfying this condition. So now use these conditions, put I is equal to 0 here, so we get first equation a naught a1 x naught a2 x naught whole square an x naught raised to the power n. This is equal to p at x naught, but according to this, p at x naught will be nothing but f of x naught, and this is known to you. This value is known to you. Similarly, put I is equal to 1, so we will have p at x1 is equal to a naught plus a1 x1. So we are writing the right hand part here, a naught a1 x1 plus a2 x1 whole square plus an x1 raised to the power. This is equal to p at x1, but p at x1 is f of x1, that's why f of x1, and so on. Similarly, the nth, put I is equal to n here, so we will get p at x n is equal to this, and ultimately we have this equation. So these are total how many equations? N plus 1 equations. So this system of equations has a unique solution, because what is our target? To show the uniqueness and existence. Okay, so this system of equation has a unique solution, or the polynomial px exists if, what is the condition? If the Vandermonde, you have, this is the Vandermonde determinant, this is denote the Vandermonde determinant v x naught x1 xn, which is nothing but the determinant of this system. If you will determine the system means, in first equation, coefficient of a naught is 1, coefficient of a1 is x naught, coefficient of a2 is x naught whole square, so listed here, and this coefficient of an is x naught raised to the power n. Similarly, second row from the second equation, and from the last equation we have this last row. So this determinant should be non-zero, and this determinant is denoted by this v x naught x1 xn and known as Vandermonde determinant. This should be non-zero. So for this, for the unique solution of this one, the determinant should be non-zero. For this, basically the determinant should be non-zero quantity. Okay, and this determinant is denoted by this, known as Vandermonde determinant. Okay, now in place of this last one xn, represent, because we want to construct the polynomial, but this is the determinant actually. So what we will do, last xn is replaced by x, last xn is replaced by simple x, variable. This is the value, however this is the variable. So v x naught x1 xn minus 1, and then last one is replaced by x. So then this determinant will be what? 1 x naught whole square x naught raised to the power n, 1 x1 x2 x1 whole square x1 raised to the power n, and last row will be 1 1 xn की जगह क्या हो जाएगा? Simple x. So xn whole square means x square, xn raised to the power n means x raised to the power n, because we have replaced xn by x. Here is xn, here is x. Okay, so that's why. Okay, so when you open this determinant or simplify this by just taking what you can do, just subtract second row by first row, third row by first row, and nth row by first row. So ultimately you will have these type of factors. So that's why we have taken and open this. So ultimately, finally, when you simplify this type of determinant, we have x minus x naught, x minus x1, x minus xn minus 1 multiply by some constant a, which is to be determined. Okay, so when you simplify this determinant, so we will get these factors multiply by certain constant a. So where a is constant. So now uh, comparing the coefficients of x raised to the power n. Compare. So here when you multiply this, how many factors are there? X naught, x minus x naught, x minus x1. These are total n factors. When you multiply ultimately these factors, highest power will be x into this, gives you x raised to the power 2. Similarly, next factor when you multiply will provide you the highest power, x raised to the power 3. Similarly, when you multiply these n factors, ultimately x into x into x into x, this will provide you x raised to the power n, which is multiplied by a. So one side we have a, and the another side will be nothing but this determinant. Here we have x raised to the power n term. So when you open this determinant with respect to x raised to the power n, so what you will do, the process is that just take x raised to the power n, remove this column and remove this row, and open this n minus 1 n minus into n minus 1 determinant. So this is basically this 1 x naught raised to the power n minus 1 up to here, and last row is 1 xn minus 1 whole square, and then here the point will be xn minus 1 raised to the power xn minus 1, this determinant. So right hand side provide you a, and left hand side is calculated with the help of this determinant, which is written here. This is another nothing but this same matrix. The only difference is there, here we have xn n, here we have n minus 1 n minus 1. So the Vandermonde determinant will be v x naught x1 xn minus 1. Okay, so this is the meaning. So now we have just substitute this value of a in equation number 2. So what we will get, this is equal to this factor multiply by a, but a is nothing but this Vandermonde representation, v x naught x1 xn minus 1. Okay, now put x is equal to xn, just replace this x equal to xn here. So v x naught x1 xn is equal to, because our target is this one, this is equal to this v x1 naught x1 xn minus 1. So this is written here, multiply by xn minus x naught, xn minus x1, xn minus xn minus 1. So these are the product. So this is in short, this multiply by this pi is nothing but the representation of the product from 0 to n minus 1, because 0 1 up to n minus 1. So we are taking the product, this product of the factors xn minus xi. So when you put I is equal to 0 here, so we get first factor, and since pi is there, so multiply. When put I is equal to 1 here, so you will get the second factor, and we are making the product. So this basically represent the product. Okay, now here apply recursively. So here you have this, once if here you will see that here we have x naught x1 xn, here we have x naught x1 xn minus 1, and this product. Now find out this value. So अगर हम इसको लेफ्ट में रखेंगे तो क्या हो जाएगा, xn minus 1, then this xn minus 1 x naught x1 xn minus 1 की वैल्यू क्या होगी, v x naught x1 xn minus 2, and then certain product is there, तो product रखेंगे तो we are having double product, like so, like do this recursively. So ultimately in the right hand side we have only products like this, there is no Vandermonde matrix, क्योंकि वो order उसका कितना हो जाएगा, 1 we have n minus 1, another time we will have n minus 2, another time n minus 3, and slowly this v will be removed and we have only products. Okay, and that's why we have this applying recursively, we get v x naught x1 xn is equal to nothing but the product of the form xi minus xj, where I and j starts from 0 to n, and condition is that I is greater than j. And since all the node points are different, just like this in this figure, if you will see, all the node points are different, so we can say that xi is not equals to xj, and this condition will guarantee you that I is not 0 in this product. There is no x naught minus x naught, otherwise the whole product will be 0. So this will guarantee you that all these xi and xj, they will be different points, and hence this product will be non-zero quantity. Okay, as xi is not equal to xj, that's why. So now we will prove the uniqueness part. So this will provide you the existence one. Now we will prove the uniqueness part. So this will provide you, since this Vandermonde is non-zero, that means this will satisfy this condition, and hence according to this the system of equations has a unique solution or polynomial exists. So this exists because this is non-zero. So we have proved that this Vandermonde is basically non-zero quantity, and we have proved here this is a non-zero quantity. Okay, so that's why, since Vandermonde determinant is non-zero, and that's why this implies Px exists. Now we will prove the uniqueness part. So suppose we have two matrices, two polynomials. So to prove that the polynomial Px obtained above is unique, so suppose we have two polynomials, one is Px, another one is P star x, which also satisfies the condition, interpolating condition, P star xi is equal to f of xi, where I is 0, 1 to n. That means P satisfies this condition and P star xi also satisfies this condition. Now consider the difference of these two polynomials, Px and P star x. This is a polynomial, this is another polynomial, so their difference will be a polynomial, and this difference is denoted by Qx. Qx is nothing but Px minus P star x. Since Px, the degree of Px is basically what? The degree of Px is nothing but n. Similarly, the degree of P star x is also n. So there the difference will be obviously a polynomial of degree less than equal to n. So that's why Qx, since Px and P star x both are polynomial of degree less than equal to n, hence Qx is also a polynomial of degree less than equal to n, satisfying the condition Q at xi is equal to P at xi minus P star xi. But since Pxi is nothing but f of xi, P star f xi is also f of xi, so their difference will be f of xi minus f of xi, that means 0. Okay, so Qxi is 0 for all I from 0 1 up to n. So what means is that Q, the degree of the polynomial, this is a polynomial with degree of Qx is less than equal to n. Number one condition. Second is what? Q at xi is 0 for all I from 0 1 to n. That means we have a polynomial with how many roots? These are the basically the roots, because right hand side is 0. Total n plus 1 roots. So we have a polynomial whose degree is less than equal to n and having n plus 1 root points. So what will be the polynomial? To understand the meaning, let's see linear polynomial. Suppose n is 1. So we have basically Qx is equals to say a0 plus a1x or b, because here we are using a, so we are not using same notation, b0 plus b1x. Suppose मैंने मान लिया कि n की वैल्यू 1 रखता हूँ यहाँ, तो आपको आइडिया लगेगा कैसा पॉलिनोमियल बनने वाला है. So n is 1 रखा, so Qx is less than equal to 1, that means a linear polynomial, so b0 plus b1 type. And according to the second condition, Q at x0 is equal to 0, क्योंकि हमने n की जगह 1 रखा है, so we are considering 0 and 1, so Q at x0 is 0, Q at x1 is equal to 0. What is the meaning? Put x equal to x0 here, so we get b0 plus b1 x0 is 0. Put x equal to x1 here, so b0 plus b1 x1 is equal to 0. So substituted x equal to x0 here, so we get this equation. And put x equal to x1 here, so b0 b1 x1 here, but q of x1 is 0, that's why we have second equation. When you simplify these two, what will be the result? Result will be just subtract these two, so this will be cancel out. So ultimately, and since x0 is not equal to x1, both are different roots, so obviously when you subtract this, so just cancel out this, so we get b1 x0 minus x1 is equal to 0. And since this condition, so this will be non-zero quantity, so ultimately b1 is 0, and when b1 is 0, so b0 is 0. Okay, so b0 is 0, b1 is 0, and hence q, this will be 0. So basically we have a zero polynomial. We will have a zero polynomial which is meaningless. Okay, so qx is a polynomial of degree less than equal to n, which has n plus 1 distinct root points x0, x1, xn, and hence q of x is basically zero polynomial, because a polynomial of qx of degree n has exactly n roots, and here we have n plus 1 roots. Okay, so that's why, and since this is 0, and hence we can say that p star x is equal to px, because the difference will provide you 0. So the interpolating polynomial, so both will be same polynomial, so this will provide you the uniqueness. So the interpolating polynomial obtained in two different ways, may be different in form but are identical otherwise. Okay, their procedure of evaluation may be different, but ultimately, or their representation may be different, but ultimately both are represented same polynomial. Okay, so depending on its form, the polynomial is called either the Lagrange's interpolating polynomial or the Newton divided difference interpolating polynomial. Okay, so now we will discuss, in the next video we will discuss Lagrange's interpolating polynomial. Okay, and then we will discuss Newton's divided difference interpolating polynomial. Okay, thank you.